Welcome to Organic Chemistry. Today, we are going to explore one of the most fascinating aspects of molecular structure, how we name the three-dimensional arrangement of atoms in space. Imagine trying to describe a spiral staircase. You need a way to explain if it twists to the left or to the right. In chemistry, we use specific designations to communicate these exact three-dimensional shapes. We will start with the historical D and L system and then move to the modern R and S system. By the end of this video, you will be able to look at any chiral molecule and confidently name its exact configuration. Let us dive in. To begin, let us look at the D and L designation system. Why does this matter? Well, before we had advanced tools to see molecules in three dimensions, chemists needed a reference point. They chose a simple sugar called glyceraldehyde. This is a relative system, meaning we describe a molecule's shape by comparing it to the standard. We draw the molecule in a Fischer projection, placing the most oxidized carbon at the top. Then we look at the bottommost chiral center. If the main functional group points to the right, it is D. If it points to the left, it is L. This might seem old-fashioned, but it is still the absolute standard in biology. Your body only uses D sugars and L amino acids. Now that we understand the concept, let us look at the formal rule for assigning this configuration. The formula on screen shows that the configuration is strictly determined by the position of the functional group on the bottom chiral carbon. The variable C refers to the final D or L label assigned to the entire molecule. The variable P represents the position of the functional group on the highest numbered chiral carbon in the vertical chain of a standard Fischer projection. If you physically swap the groups on that specific carbon from right to left, the entire designation flips from D to L. It is remarkable that in a massive molecule, just one specific carbon dictates the name of the whole structure. Before we move on, let us see this with a concrete example. We will determine the configuration of glyceraldehyde itself. We are given a Fischer projection. First, we must verify that the molecule is drawn correctly. The most oxidized carbon, which is the aldehyde group, must be at the very top. Next, we need to locate the lowest chiral center on the vertical chain. Since glyceraldehyde is a simple molecule with only one chiral center, we simply focus our attention on that middle carbon. Finally, we identify the position of the defining functional group, which in this case is the hydroxyl group. We need to see which side of the vertical line it sits on. Continuing with our glyceraldehyde molecule, we observe the position of the hydroxyl group. Because the hydroxyl group is clearly drawn on the right side of the vertical carbon chain, we can apply our rule for the D designation. Therefore, this specific molecule is officially named D-glyceraldehyde. This final answer tells any chemist in the world that its three-dimensional shape matches the right-handed reference standard perfectly. It is a simple but highly effective way to communicate molecular geometry without needing complex three-dimensional coordinates. Now that we have used this formula on a simple molecule, let us apply it to a much larger and more complex one, glucose. Glucose has 6 carbons in a vertical chain. We start by verifying the aldehyde is at carbon 1 at the top. Next, we locate all the chiral centers, which are at carbons 2, 3, 4, and 5. With multiple chiral centers present, students often get confused about which one to look at. The rule strictly states we must look only at the highest numbered chiral center. This is always the chiral carbon furthest away from the top. In the case of glucose, this critical carbon is carbon 5. Continuing with our glucose molecule, we focus entirely on carbon 5 and completely ignore the hydroxyl groups on carbons 2, 3, and 4. We observe that the hydroxyl group on carbon 5 is drawn on the right side of the vertical line. Since it is on the right side, the entire molecule is designated as D-glucose. Even if all the other hydroxyl groups were pointing to the left, Carbon 5 is the only one that dictates the D or L family. This specific D-glucose is the exact form of sugar that circulates in your bloodstream right now, proving how a single carbon determines the biological category of a large molecule. So, we have seen how the relative D and L system works. This brings us to the R and S designation, which is an absolute system. Why do we need a new system? As molecules got more complex, scientists realized a relative reference was not enough. They needed universal rules that could describe the exact shape of any chiral center without comparing it to anything else. Think of it like the steering wheel of a car. Turning right is an absolute direction, regardless of what city you are in. This system is absolutely critical in the pharmaceutical industry. The R and S versions of a drug can have drastically different effects in the human body, sometimes meaning the difference between a cure and severe side effects. Now that we understand what the absolute configuration is, let us look at how it works mathematically. To use the R and S system, we must first assign priorities to the groups attached to the chiral center. This formula shows that priority is directly proportional to the atomic number, represented by the letter Z. This means that as the atomic number of the attached atom increases, its priority increases, giving it a better ranking, like 1 or 2. The atom with the highest atomic number gets priority 1 and the lowest gets priority 4. If two atoms have the exact same atomic number, you cannot stop there. You must move outward along the chemical chain to the next atoms until a point of difference is finally found. Let us see how this works in practice. Before we move on, let us see this with a concrete example. Let us determine the absolute configuration of a specific chiral carbon in a simple molecule, 1-bromo, 1-chloroethane. We are given a central carbon atom attached to 4 different groups: a bromine atom, a chlorine atom, a methyl group, and a hydrogen atom. Our first step is to assign priorities 1 through 4 based strictly on their atomic numbers. We look at the atoms directly attached to the chiral center. Bromine has the highest atomic number of 35, so it gets priority 1. Chlorine is next with an atomic number of 17, getting priority 2. The carbon of the methyl group has an atomic number of 6, making it priority 3, and hydrogen is lowest at 1, making it priority 4. Continuing with our molecule, now that we have our priorities, we check the physical position of the lowest priority group, which is hydrogen. The problem states it is already pointing away from us on a dashed wedge, so we do not need to mentally rotate the molecule. We can directly trace the path from priority 1 to 2 to 3. This path moves in a clockwise direction, just like the hands of a clock. Because this clockwise motion directly leads to our final answer, the absolute configuration of this chiral center is R. This tells us the exact, unambiguous 3-dimensional arrangement of the atoms in space. Now let us look at a slightly harder molecule where we encounter a tie, 2-butanol. The chiral carbon is attached to a hydroxyl group, a hydrogen atom, a methyl group, and an ethyl group. The hydrogen atom is pointing away from us on a dashed wedge. We start by assigning priorities based on atomic numbers, just like before. Oxygen has the highest atomic number, so it is priority 1, and hydrogen is priority 4. However, we have a tie for priorities 2 and 3 because both the methyl and ethyl groups attach to the chiral center with a carbon atom. We need a systematic way to break this tie. Continuing with our tiebreaker, we must look at what those specific carbon atoms are attached to next. We list the attached atoms in decreasing order of atomic number. The ethyl carbon is attached to 1 carbon and 2 hydrogens. The methyl carbon is attached to 3 hydrogens. Now, we compare them one by one to find the first point of difference. Comparing the first atom in each list, the carbon in the ethyl group has a higher atomic number than the hydrogen in the methyl group. This single point of difference is all we need to make our decision. Now that we have broken the tie, let us find the final result. Because the ethyl group won the tiebreaker, It gets priority 2, and the methyl group gets priority 3. Now we trace the path from the hydroxyl group at priority 1 to the ethyl group at priority 2 to the methyl group at priority 3. This path moves in a counterclockwise direction, opposite to the hands of a clock. This counterclockwise motion dictates our final result. Therefore, the absolute configuration of this specific molecule is S. We have successfully broken a tie and determined the exact geometry of the molecule. Now that we have calculated these configurations, let us visualize exactly what we just found. On the screen, you see two tetrahedral carbon atoms. Notice how the lowest priority group, labeled 4, is placed on a dashed wedge, meaning it is pointing away from you, into the screen. This is the crucial steering column perspective. On the left, tracing from group 1 to 2 to 3 creates a clockwise circle, which gives us the R configuration. On the right, tracing from 1 to 2 to 3 creates a counterclockwise circle, giving us the S configuration. This diagram perfectly summarizes the absolute, unambiguous way chemists communicate three-dimensional molecular shape. We have covered a lot of ground today, so let us summarize the key takeaways. First, we learned about the D and L system, which is a relative naming method based on comparing molecules to a standard glyceraldehyde molecule. It is determined by the bottommost chiral center and is essential in biology. Second, we explored the R and S system, which provides an absolute configuration using Kahn-Ingold Prelog priority rules based on atomic numbers. Finally, we saw that after pointing the lowest priority group away, a clockwise path means R and a counterclockwise path means S. You now have the tools to confidently determine the three-dimensional configuration of chiral molecules.